Hi, so in the previous video I discussed the path dependence of a line integral. So now I'm going to show you that under certain conditions the path does not in fact matter. So let's find out when it does not matter. So you might remember the fundamental theorem of calculus. The fundamental theorem of calculus says that if you integrate a derivative, this is the same thing as evaluating the endpoints. Okay? Now sometimes you'll see people write it with a capital F. Like this, okay? I don't really care if you use a capital F or a lower F. They're trying to suggest something. They're trying to suggest an antiderivative. But really, look, it's just a letter, okay? So the point is, if you have that function's derivative and you integrate it along A and B, you can evaluate it by plugging in A and B. Okay, so I'm going to compare it now to a similar equation. This is the fundamental theorem for line integrals. So this says that the integral of the gradient along C is going to equal this, provided C is smooth and loops. Okay, so provided it is smooth and loops. So what do I mean by smooth is that it doesn't have any kinks in it. So for example, the absolute value function, f of x equals the absolute value of x. This is not a smooth function because it has an edge, right? And so when I take the derivative of it, the derivative on the left is -1 and the derivative on the right is +1. And so we say that this function is not smooth, okay? So officially, a function is smooth if all of the derivatives exist and they are continuous. Don't worry about that for this class. For your purposes, in this class, you can assume everything is smooth, okay? All curves are smooth, so don't worry about it. In fact, this is the attitude that most physicists and engineers have. Everything is smooth. Okay, what do I mean by loop? I mean that the starting point and the ending point are the same. So in the previous example, I had these 2 points, right? And I considered this path here, right? This I called C1, and then I took this other path. I took this other path, and it was C2. Okay, well, notice that the starting and the ending point were not the same. So these two integrals were different. But if I, in fact, said that C was just the whole thing, right? Starting here, you go up, then you come down. That's going to turn out to allow us to use this equation. Okay, that's all I'm saying. I'm saying that if the path is circular, in some sense circular, okay, could be shaped like a square or a triangle, but I just mean that it's coming back, it's a loop. If it's like that, then I can put in that form. So what is the b and the a? That's just the time, right? So if I have a loop like this, right, all I'm saying is that the time it took me is different, right? So I start off here, I go this way, right? And my initial time is time equals a, right? So t goes between a and b. Think about the unit circle, right? It starts at 0, or sorry, the theta value starts at 0 and it ends at 2 pi, but in both cases it ends at this point, right? It's really no different. There's this path you're taking and t is going to change, or in that case theta. Okay, so you might say, well, why is that true? I want to go ahead and show you why it's true. I don't normally do proofs in this class, but I think it's helpful in this case. So you have this integral. Here it is. And when we convert this based on material from the last section, we're going to rewrite it in the vector form. So the vector form looks like this, right? So I take my f, and I'm going to parameterize the position of f as a function of space, where the positions are described by r. Now r, t, is a vector x of t, y of t, z of t, right? It's just the x, y, and z components as they relate to time. So if I take the derivative of this with respect to time, I should get dx, dt, dy, dt, dz, dt. Okay? And as a refresher, this del f, gradient f, del f, however you want to say it, it is the partial derivative of f with respect to x, the partial derivative of f with respect to y, and the partial derivative of f with respect to z. So I can take that information there, and I'm going to rewrite this equation here. So I still have my AB, and I'm gonna rewrite this. So this is going to be based on this equation here. Now, yes, there is a RT input. You can see it right here. It's in there. It's hiding. Okay, but this is still true. It's still with respect to taking the derivative with respect to x or y or z. So I get del f, del x, del f, del y, del f, del z, and I take the dot product, and I just took the derivative of r, so I'm going to write it over here now. So I get dx, dt, dy, dt, dz, dt, dt. And this is going to equal, just by taking a dot product of two vectors, it's going to equal AB del f del x dx dt plus del f del y dy dt del f del z dz dt dt. Okay? So that's what we have. The final step, or nearly the final step, I'm just going to rewrite all of that with dt, d dt, f r t dt. Now this is maybe the step that's hard to see, but it's not too difficult. So basically this is the chain rule. Okay. Okay, so it's the multi-dimensional version of the chain rule. So let's see why. So if I want to get to t, I have to basically go through all the paths to get to t. So t is contained in x, it's contained in y, and it's contained in z. Well, f is a function of x, y, and z. Okay, so this is the outside part, right? What is chain rule? Derivative of outside times the derivative of the inside. But in this case, there's three insides, right? There's x, there's y, and there's z. So the way we do that is we explore all possibilities. We take the derivative of f with respect to x, multiply it, so this is outside, inside, plus outside, inside, plus outside, inside. We're basically exploring all the insides, right? Okay, good. So I'm writing that. Now, the final step is you apply the fundamental theorem of calculus. So what is this going to say? Well, this is a derivative, this is an integral, so I'm just going to plug in those points. So this is f r b minus f r a, and I'm done. That's it. So this part right here, the chain rule, the multi-dimensional chain rule, this was discussed in the section on optimization, but we skipped it in this course. I don't mean to frustrate you because, yeah, we skipped it. But just know that that's why it happens. If that bugs you, the simple answer I want to give you is don't worry about it. Technically, all you need to know is these two parts. So, strictly speaking, you could skip this video, but maybe one day you go back and you can watch it again. This will make more sense. Okay? Good. See you in the next video.